So I think all committee members are here, right? Dr. Gordon
Yes, hello.
and Dr. Wu,
Yes.
Dr. Wu, and myself. So if you don't mind, I'm just gonna go ahead and introduce Tim, and he's gonna take the podium. First of all, thank you everybody here for joining us today for Timothy Grandin's thesis defense. Tim is originally from Arlington, Texas, and he got his bachelor science degree in aerospace engineering in 2013 from Embry-Riddle Aeronautical University, Daytona Beach. Like he was commissioned as an officer in the U.S. Navy since 2013, and he went through flight training, and he has more than 1,000 combined flight hours with MH-60 Nighthawk helicopter. He has 3 pending patents for an unmanned systems and many other accomplishments. He is married with 1-year-old daughter and currently resides in Panama City Beach, attached to Naval Surface Warfare Center at Panama City Beach, and he serves as the UAS program manager and air operations department head. And Tim and I met almost 2 years ago, right? He took a course with me, and since then we have been working together for his master degree. And Dr. Gordon is we are basically co-chairing his study with Dr. Gordon, and Dr. Wu is the committee member. And with that, I think you can just proceed and continue. Podium is yours. Thank you. I guess you are muted, Tim.
All right, thank you, Dr. Yavis. I appreciate the introduction. And without further ado, we'll go through the design and mechanical characterization of functionally graded sandwich beams through additive manufacturing. All right, we're going to talk about a little bit of background. What are sandwich beams and what is a functionally graded material? We'll go over current state of literature that'll lead us into our research approach. We'll briefly go over an overview of the research and then cover how the mathematical hypothesis was formed, the model geometry, the finite element analysis simulations that we completed, and then our experimental method, and discuss the results. And then if you have any questions, feel free to ask me whenever. Otherwise, we'll have time at the end as well. All right. So sandwich structures have been around forever. As you can see, they're naturally occurring in nature. We've got a sandwich structure in the skull. A sandwich structure itself consists of a lightweight core material surrounded by face sheets. In industry, that's going to mean some kind of like honeycomb or foam core surrounded by like either a metallic or composite face sheet. And in literature, this is commonly compared to that, the geometry of an I-beam, where the flanges or the face sheets take the majority of the loading, and then the wib or the core material increase the moment of inertia for bending stiffness. This can be seen down here in a loading example, 3-point bending, which you're gonna see through the experimentation we do. You have the load applied directly in the center, and that load is transferred from bending into the compressive force on the top skin and the tensile force on the bottom skin. Early examples in aviation, we obviously want lighter means faster, higher, and going further. So sandwich structures were introduced in the Mosquito in World War II, British aircraft. These sandwich structures were composed of a balsa wood, which is a core structure, which is extremely lightweight, and surrounding thicker plywood face sheets to give it that stiffness. And you can see a modern sandwich structure composite with a honeycomb structure in the center surrounded by carbon fiber face sheets. Major advantages of this include both strength and stiffness to weight ratio, as well as secondary advantages, which would be like thermal absorption, vibration, dampening, and acoustic dampening as well. All right. A lot of literature started coming out during the space race. In the 1960s, NASA was trying to develop things to go to the moon. We wanted to go faster, we wanted to go higher, we wanted to go further. So in doing so, there's a lot of research done in sandwich panels, specifically honeycomb. In the upper right-hand corner, you can see the Apollo capsule, which eventually took us to the moon, was comprised of an outer skin of stainless steel with a stainless steel honeycomb all through the heat shield and outer, and then the inner structures were primarily aluminum honeycomb with aluminum face sheets. In 1969, NASA contracted General Dynamics to combine all of these works that had already been done. And you can see Sullins, who was working for General Dynamics, composed a paper that served as a design manual to cover flat plates, cylinders, cones, domes, and cutouts, all related to sandwich structures. And then moving forward in 1999, Ashby and Gibson wrote the book Cellular Solids, which served as the combining all the fundamentals of core materials, face sheet materials, manufacturing methods. And of note, they classified those into two groups. We have planar, which is going to be 2D structures, which we'll be talking about today, and spatial lattices, which are 3D structures, sort of like the foams or other 3D lattices. And then in the lower right-hand corner, you can see where Gibson and Ashby first categorized the performance factor for sandwich panels. On this graph right here, we have the flexural modulus. So that's going to give us eventually our flexural stiffness, or the flexural Young's modulus there too. And then the density lines down here. So density goes up, the weight of the structure goes up. And then we have these dotted lines going through, which are actually our performance factor. And this is going to be E to the 1/3 over rho, which is the Young's modulus to the 1/3 over the density. The 1/3 is specific to sandwich panels. And then we'll be using 1/2 today, E to the 1/2 for sandwich beams in specific. So looking at this graph, we've got our heavier alloys up here. They're going to have an excellent flexural modulus. We got your aluminum 70-75, 60-61, and then your steels over here. And then coming down in the lower left-hand corner, we've got all our rigid polymers. So we've got PVC cores, other different types of plastic cores and foam cores. And if we combine both of these in a sandwich panel, where the higher stiffness is on the outside and then the lighter weight materials in the core material, we have our optimized region up here. So we're moving higher in our performance factors, and we're able to optimize based on skin thickness, materials, and core thickness of materials to get our enhanced in performance. Moving forward in the year 2000, Hexel, who's a manufacturer of core materials as well as other composites, created a manual summarizing the design methods specific to their panels, in which the face sheets and the core material are specifically bonded with adhesive layers. Failure modes and how to avoid these failure modes in both manufacturing and design were also discussed. And in 2002, Daniel published specific literature dealing with these failure modes. As you can see on the right-hand side, we have specific failure modes, a few of them, with the force loaded in the center, and in 3-point bending with 2 supports on the outside. You have face yielding, in which the force from the top actually yields those based on those tensile forces that are distributed in the lower face sheet. Face buckling from the compressive forces in the top, and then core failure, either due to shear or pure compression. These modes were specifically addressed with aluminum honeycomb core material, as well as PVC foam cores and unidirectional carbon fiber skin faces. And face sheet wrinkling, compressive failures in the faces, adhesive failures in which some of this would peel up, and then core failures were addressed. In the lower left-hand corner, you see depictions with strain lines of impact loading, skin buckling, and their experimental data was compared with mathematical predictions. And then in 2007, Ashish predicted deflection in those beams and compared his theory to experimental data as well. All right, moving forward into functionally graded material. Functionally graded materials were originally the idea originally came out in 1972 by Bever as gradient composites, and then coming forward in 1994 at the International Conference for Composites, they were given the name that has stuck since then, which is functionally graded materials. In 2020, Sele conducted a comprehensive research review, including processing methods and different forms. A functionally graded material itself is different from that sandwich panel, and the density changes throughout. Examples that occur in nature are going to be human bones. You can see where we connect to the pelvis here. You got it completely hollow down here, and then we're gaining density as we come to the face, the outer walls, and different throughout the entire structure. When we go look at bamboo, we can see a microscopy zoom in of the actual cells in the layers, and you can see that the cells are a little more sparse and they get more dense as you get to the outer face in here. In Saleh's review, he discussed different manufacturing forms that are listed in the inner circle here. Primary method we're going to be looking at today is going to be additive manufacturing, but other methods include combining two materials, as well as combining the density of one material that comes out. Different types are discussed on the outside here. We've got low density and high density. We've got thick being sandwiches, or thick being large plates. And then we've got thin, which is more of a surface coatings. All right. And coming forward, Stille in 2021 investigated buckling and post-buckling analysis in functionally graded thin plates that were subjected to various loadings and various boundary conditions. Utilized the classical von Karman thin plate kinematics and the asymptotic numerical method to investigate these, and then compared his results to numerical analysis or finite element analysis. And the results were based upon a 5-layer laminate, as well as aluminum and aluminum oxide functionally graded cores. And the aluminum oxide functionally graded core you can see here in finite element analysis in a clamp situation. And then in 2022, Bandahari specifically addressed an issue that was common to functionally graded materials that were that have been produced in the past. He specifically addressed crack tip stress fields and dynamic stress intensity factors and crack growth throughout these materials. Cyclic mechanical loading, cyclic thermal loading, as well as impact loading were all addressed. And it was found that the cracked functionally graded plates actually exhibited a higher fatigue life when compared to that of their equivalent composite plates when subject to the same loading and boundary conditions. However, in the lower right-hand corner, you can see a picture of the thermal loading cycles on the bottom, and then the actual crack length. Then you can see that functionally graded materials do not perform as well when subjugated to thermal loading properties. All right, and now combining the two, we've got functionally graded sandwich beams. In 2000, Sanker utilized the Euler-Bernoulli beam theory to develop equations for transverse shear loading. He introduced a sinusoidal transverse loading to theoretical functionally graded beams and developed an elastical solution. In 2006, Avila produced the samples in the upper right-hand corner. You can see right here we have fiberglass reinforced plastics for the skin, upper and lower faces. And then you can see the foam core, how it's actually functionally graded from low density to high density. He was on all of these, they were asymmetric, going linear from low density to high density or high density to low density. And it was found that there was no significant bending stiffness increase in the asymmetric core materials. The highest performer, however, was putting the highest density foam at the top, and this reduced normal wrinkling stresses or increased the wrinkling stress that it could take in the upper surface, as well as decreased core plastic collapse. In 2014, Sharma developed mathematical solutions for both the displacements as well as core stresses in functionally graded materials, and he verified his elastic equations through finite element analysis. And then moving forward to 2021, we're getting closer to our research. Derek Vand utilized sandwich panels that were composed of, or sandwich beams, excuse me, composed of ceramic cores as well as ceramic face sheets. And he specifically researched 3 different areas looking for critical buckling loads. If you look in the lower right-hand corner, he looked at uniform porous density in the ceramic core, symmetric non-uniform, as well as asymmetric non-uniform. It was found that the critical buckling load for the asymmetric pattern, or the bottom one, was actually the highest out of all these 3 three methods, and he utilized the differential transfer method to develop this conclusion. This method proved efficient and reliable, and has been employed in functionally graded solid mechanics sense and referenced in other works to date. All right, now functionally graded additive manufacturing, which is how we're going to produce our panels today, has been researched in the past, and there was a comprehensive review by Zhang in 2019. He looked at different methods of manufacturing and outcomes of experimentation. Lens, SLA, functionally selective laser sintering, and other methods were investigated. And in the right-hand corner, you can tell that to this date, most research that has been conducted has been using different specific layers of density or different specific layers of materials that were printed on top of each other. Issues with this, there's cracking in between the layers, as you can see from the right side here, which led to materials that weren't very repeatable and weren't very reliable. He also talked about material jet process printing, which is the same as polyjet printing, which we'll be talking about later and utilizing for our project today. Polyjet printing basic overview, which we'll go into more later. A powder goes down, it's rolled over with a roller, and then it's cured either thermo cure cycle or with UV curing or other methods. On the right hand side, you see samples of the functionally graded materials produced on a polyjet additive manufacturing technique, and you can even see the layer lines in there from where the different densities went up. All right, so polyjet specific stuff. We've got two specific people we're going to talk about with similar research, but different findings. Kazan in 2014 produced two different samples, 9 each, on an Objet Eden 330 and a full cure 720 material. He was specifically addressing tensile testing for ultimate tensile strength, as well as surface roughness. His sample and printing orientations are shown right here in the lower left-hand corner. And they were all printed with solid, as solids. There was no change in density, there was no change in core. And in his findings, he noted that the x-axis, or samples 1, 2, and 3 right here, proved the most deformation resistant. So they came out the most with the highest accuracy, and they also had the highest strength to them when he put them through tensile testing. In 2012, Barclift conducted a similar experiment with a similar layout. However, he found that the proximity on the bed was also played a factor. The age of the print was a factor, which led us to making sure we crushed or processed our samples all on the same day. So there was no discrepancy there, and that the z-axis proved to be the least accurate, or the samples 14 through 18 right here. You can see his outcomes right here for tensile strength as well. And this also influenced our research, and we didn't print any in this orientation. And this builds up to our research method. All right, so we have two novel concepts that we're proposing here. Our first objective is that we can produce these sandwich panels or sandwich beams in a single manufacturing process using the printer over here in the lower left-hand corner, a Stratasys J55. Second being that we can further increase the sandwich stiffness to weight ratio by functionally grading the core, an example being in the lower right-hand corner. Both of these will be proven utilizing 2D triangular core geometry in the PolyJet Stratasys J55 machine. And we're going to show and quantify the increase in stiffness to weight ratio mathematically, and then prove it through numerical analysis or simulation, and then prove it experimentally. And the importance of this, our motivation, we know that the aerospace industry is willing to pay $10,000 to $20,000 approximately per pound of stuff that they send into orbit. So if we can lose a couple pounds, that means by increasing the stiffness to weight ratio where necessary, that means we can put either more guidance fuel there on satellites, or decrease the cost to get the satellite up there, or increase the lifespan of the satellite by being able to put more resources on board. This is also secondary significant effects on high performance aircraft, F1 cars, and other high performance vehicles in racing. Okay, so in our hypothesis, our first main goal is going to be the formulation of a flexural modulus for functionally graded beam. So we're going to start with the control sample, or come up with something for the uniform core. In doing so, we're going to use a couple common variables throughout this presentation. T is going to be the thickness of the face sheets. C is going to be the height of the core, and Z is going to be where in the core we're talking about. L is going to be the length of the sandwich beams in question, while B is the width and D is the height. And then EC and EF will be the Young's modulus of the core material and the Young's modulus of the face sheet. One thing to note, since we're utilizing the same material for the face sheet as that the core is made out of, we're able to combine those two and put the Young's modulus of the core in terms of the face sheet and substitute that back into our equation series. So to start out, we're going to start with the Euler-Bernoulli classical beam theory for effective modulus, or EI effective, and we're going to integrate that. And then we're going to, as previously discussed, we're going to take the core density and the face sheet Young's modulus and come up with a new EC, and then combine that into our equation for the core modulus. Now we need to functionally grade that. We need to change the density equation based on our density inside the core. To do so, neutral axis is going to be where the least loadings, right? So that's where we're going to want to start removing material. To make it easy on ourselves, both in calculation as well as manufacturing, we're going to do a linear variation of rho 1, which is going to be the density at the neutral axis, as it goes up to rho 2, which is going to be density right before you get to the face sheet, because all the face sheets are going to be 100% dense, right? So that's going to go from linear up to 100% density. So that's not going to be considered in our equations for coming up with the core. All right, now that we have that, our next goal is going to be to vary the density. All right, and varying the density, we're going to start with the density of the core at the neutral axis, which is going to be rho 1, and we're going to add that to the density by the face sheet minus the core that's already in there. And then we're going to vary that with Z as it relates to C. You can test this really easy. If you put in 0 for Z, that's going to be at the neutral axis, and that's going to give you the neutral axis density. Or they're going to take that, plug it directly into the equation we already found for EC, or the core Young's modulus, which is now varied, and then plug that back into EI effective, or effective core modulus, and integrate and come up with our variable equation now to be compared with the constant equation, which is our control. All right, now we need to get rid of geometry. We need to take that out of the equation. So we're going to normalize it by the second moment of inertia. Second moment of inertia is going to be purely based on the geometry that we discussed earlier. We're going to divide that out, and we're going to get E effective, or the effective Young's modulus. And now that we have that, we can start to visualize this and plot this through MATLAB and get the variation of effective flexural modulus for functionally graded chord sandwich beams. You can start to, so over here on the Z-axis, you can see this is going to be the effective Young's modulus in pascals, and then that's going to be varied with rho 1, or the density near the neutral axis, and then density near the face sheet over here. And then you can start to pick out where our design space is going to be, where we want to target our design. So taking this over 1.0 for a factor. But we need to quantify performance increase. So to do so, we're going to make a performance factor for the actual bending. We're going to take the effective Young's modulus to the 1/2, right? Because we're doing beams. We're going to divide out the density. We're going to normalize by the density, and the density being the density of the control subject as a function of the face sheet, and then our functionally graded density, or variable core density, VCD. We put those back in, and we get our performance factor for each respectively. Now that we've got each of the performance factors, we can plot those against each other and get our performance factor ratio, R. So this is the variable core density compared to the control subject, and that gives us a graph of our performance or design space. So rho 1 is going to, again, the neutral axis, and we can take that up to our beautiful density lines up here. One example, we can take this up to rho 2 of 0.4, so a 20% core density near the neutral axis up to a 40% density near the face sheet, and that gives us a 1.2 or 20% increase in performance. And for reference, our analytical model is going to come in at 33.1%, so somewhere around here, but we'll get there in a second. First, we got to make a model. All right, so in developing the geometry for the model, we want to consider our design parameters. We know we're doing 3-point bending testing. We know we want to have at least 2 cell density layers, 2 cells per density layer, cell wise, to prove our point. And then we need to come up with some cell geometry. We eventually went back to Gibson and Ashby and went with a readily available equilateral opposing triangle in the upper left-hand corner here. For the actual geometry that we would end up varying. And then we went through our manufacturing constraints that we had with 2 different printers we were deciding against. And manufacturability, ease of design, and calculation were all factored into how we would actually vary this density. So now we've got the geometry decided on, we have options. We can either vary the material, which we found doesn't work very well. You get a lot of cracking. We can vary the infill, which would be extremely complex and hard to prove and hard to visualize. We can vary the strut or wall thickness, meaning we can vary the thickness of each one of these as we go to the outside of the density. We can vary the cell geometry, which would be extremely complex because now we're going from this and we're combining, all right, now a square, now a rectangle. That get a little crazy and extremely hard to calculate, extremely complex. And then we can vary the cell size, which that's what we chose. All right, so in varying the cell size, we started by implementing parameters into our CAD software. We cut it in half because we knew we were going to mirror it across the neutral axis. You can see over here, it's an exact mirror. And then just to get this out of the way, the definitions, we're going to call this right here our middle density row. So when we refer to density row, we've got the middle, we've got the second density row, and then we've got the outer density row, which is going to be the highest density. We then split those into 3, where we cut the triangle height in half each time. And then we decided on a wall thickness of 0.02 inches based on the design manual for the 2 printers that we had. And then eventually the PolyJet printer that we came up with. And that would be the same as 0.5 millimeters. And that is uniform throughout. All right. And now for the outer geometry, we utilize ASTM standard D7250, which is the standard practice for determining sandwich beam flexural and shear stiffness. So exactly what we wanted, right? We utilized a length of 6 inches, a width of ½ inch, and then a height of the core of 1 inch. And then when combined with both face sheets, we get the 1.08 inch overall height, with each face being 0.04 inches. That gave us a neutral axis density of 27.2% and an outer density of 76%. And now we have numbers. We can actually put this back in. We just need to come up with a control. So because we half these each time, it was easy to come and just fill that whole thing in with 76% dense triangles. The variation can be seen in the center down here. We've already defined the density rows, and they can be seen with the 27%, and then coming all the way to the 75.9% on the outer one. All right. Now that we have that, we can plot our new design point. As we said before, we put a new line in here of 0.76 in MATLAB, and we took our 27% and we came out with a theoretical increase of 33.1% gain in flexural stiffness. What we did not examine here, what we're leaving for future work, is going to be taking this further and using a different combination of face sheet thicknesses and core thicknesses to further improve this performance factor. That'd be a little much to get this done in here. So, but moving on, now that we have our 3D model, we can take that and we can extract a DXF file and import it into Abacus 6.13 for finite element analysis and a simulation through the computer. We set our model as isotropic properties, linear elastic, and inputted Vero draft gray material, which is what we're going to be utilizing. It's the cheapest, most economical, and it was available in the UCF print lab. All right. That material has a Poisson's ratio of 0.4 and a Young's modulus of 2.2 GPa. And for a mesh, we set up quadrilateral elements in plane strain, and we set up 2 sets. Our loading set, which was based on a displacement of 1 millimeter and ramped up, applied right here. And then to simulate 3-point bending, which we're going to be doing experimentation, we have our clamps over here, which are set as rotation only around their points. And then we selected a couple different nodes in there to base these off of. As you can see, we ultimately ended up with a 4-element wide mesh, but we'll talk about that in a second. The field outputs that we knew we wanted were going to be displacement and reaction forces with time as we ran this through simulation. All right, so to have an accurate study, we conducted a mesh convergence study. We started with a mesh size, global seed size of 0.5 millimeters, and that gave us a 2-element wide mesh, which conforms to industry standard. But science, since we're doing this, we want to be as accurate as possible. We went ahead and explored those numbers further with 6 different meshes after that, and ended up coming up with a mesh size of 0.325 millimeters, which is about right here, 25,000 elements. With the available computer PC resources, we're able to increase our accuracy as much as possible as we came up to this converging line. All right, and now, once we ran that, we came up with our results. They can be seen down here. We got our force versus our displacement, and we plotted both of those here for our constant density as well as our variable density. And you see these are nearly linear. We went ahead and extracted the slope from each of these lines for the constant and variable right here. And then we utilized the equations from ASTM standard. This M is not the performance factor. Only this once I promise, we're going to change it to the slope like we've seen before. We're going to put both these slopes in to get the Young's modulus of the beam. And now we've got the 5.9 MPa for the constant density Young's modulus and a variable density Young's modulus of 3.8 megapascals. This gives us a performance factor of 1.319 or 31, almost 32%, which is a percent difference of 3.7 from our theoretical value. So we're doing pretty good so far, right? Now just to visualize these, we can go ahead and zoom in on where the loading occurred right here or right here. And you can see where all the compressive forces are in this dark blue region, and then our tensile forces. So that's all getting carried, as we talked about before, by the face sheets. And then you can see that kind of tapers off to pretty much nothing at the neutral axis. So let's get rid of that material at the neutral axis. We're going to go ahead and make our variable density model, run that through, and you can see, again, there's all our compressive forces, there's all our tensile forces, and you can see they maybe dip a little lower into the structure right here. All these are the axial stresses in the S22 region in FEM. And now let's put those back onto our design space. So when we go to plot this, you can see, again, these points extremely close together, meaning we're doing pretty good so far. So now let's make sure you have a good thesis when you take this, when you do some experiments. So again, we're utilizing the Stratasys J55. It's got an accuracy in the z-axis of 18 microns and an XY accuracy of 0.1 millimeters. Using Vero Draft Gray, we went ahead and imported our 2 different geometries into GrabCAD Print, which is their slicing software, and had 8 samples total. As we saw in some of the literature review, some of these printing orientations varied, so we went ahead and covered our basis. We've got 2 of each. We've got 2 flat printing oriented, functionally graded cores, as well as constant cores, and then we've got 2 vertically oriented constant and functionally graded cores on our circular building bed. Of note, this differs from the printers that were used in the literature research, as these actually rotate kind of like a microwave inside here and then come up and build your layers. You can look from here, the actual printing head is going to be the first thing that the print bed sees. As this is rotating around, the print bed is going to go ahead and expel the actual print material onto the print bed, as well as the support material if necessary. And then it's going to get hit by this roller as it keeps rolling around, and then finally cured by UV light here. You can see our vertical and flat over there right after printing is complete. And then if we look a little closer at these samples, you can see almost luminescent with the UV light white area on there. That's actually SUP 710 or the support material. If the geometry was bigger, or if there were no holes in it, we'd be able to get away without support material. But now we've got support material that we need to get rid of. All right, so in post-processing, normally you could just push this out, but since we've got such fine geometry in here, and we also don't want to destroy our geometry, we literally took this printer to its limits. we went with the secondary method, or a caustic bath solution with sodium hydroxide, easily available on Amazon. And we created a 2% solution in warm water from the lab faucet and left it in there for 2 hours. After 2 hours, we shook each sample. We got all that stuff out, and you can see right here, all that white stuff that came right out of the sample. And then we couldn't get it all out, but it was determined that the remaining material, once we pushed on it with a small pricking tool, we determined that was mechanically disconnected. It was going to come out pretty easily, which you'll see oozing out in some of the videos for the experimentation. All right, once that was completed, we let it dry for 30 minutes, put our next samples in the bath, and then we went ahead and painted these samples over with a flat white paint and then black speckling for future digital image correlation processing. All right, in the lower right-hand corner, you can see on some of the finest density row that it cracked a little bit, but that actually helped us pick it up in the DIC correlation with the camera. All right, now our experiment setup consisted of an Instron Ultimate Tensile testing machine. We took off the tensile testing jig and we put on a 3-point bending jig, as you can see right here, with the support pins spaced 130 millimeters out, and centered it as best as we could. And then put the loading pin, and then we applied a preload, which was less than a Newton. We just want to make sure we were starting from actual zero and we didn't have any dead data in there. You can see my beautiful cracked phone back there that served as a great timer. Suspended by duct tape right here, we're able to capture it in the frame and have a 2-second interval show up on our pictures that we're taking. Out here, you see an LED light, which is going to help us pick up for post-processing, help us see that in the digital image correlation. And then we manually took a picture every 2 seconds on the EOS 30D Canon DSLR camera, which was set up about 2 feet away. This was uniform throughout the runs. It did not move. And then that data was collected on our machine shown on the right. And we're able to capture the data from the load cell, as well as the displacement data from the machine, plot those, and get some good stuff out of it. All right, so it's a video of our experimentation. It's going to load here in a second. Sorry about that. All right, you can see pictorial time lapses on the left and right of both the constant and the variable density for the first and second run. We applied a rate of displacement of 2 millimeters per minute. And if you look right here, you can see that oozing we were talking about. That's that SUP 720 material coming right out of there. So yeah, mechanically disconnected. All right. So initially, we were a little let down with our results. We're showing an original 94% performance factor ratio. So we took everything, literally put it under a microscope. We took some fine, expensive calipers, and we did some measurements. It was found that the strut thickness in the lower density regions averaged out to our anticipated 0.02 inches. However, the density which served in the entire constant density sample, as well as our highest density layer by the face sheet, was 0.028 inches, which is almost an increase of 40%. And now having that increase of 40% here in the functionally graded system was factored in, as well as the massive increase in not only like material, but strength of this item, which was skewing our results. We took those increases in cell geometry, converted that to the volume, converted that further to the increase in density, and then the change in the Young's modulus for the core material. All right, right here you can see the first run coming out. We're comparing this to our FEA right here, and see linear elastic. This goes up to failure, but you don't actually see the failure because it was catastrophic. It snapped, went out of frame, and we weren't able to capture it, but pretty close right here. Then our variable core density, you can almost pick up on the core shear here, how that's kind of different. So in the center density row, that is. And then at the end, you can see how this one fails and ultimately leaves the screen. So this core shearing right here is going to be different from our model, but we're going to talk about that a little later. Now, let's take the data we got. So in this data, we've got the force versus displacement for both build orientations. And you can tell that the uniform core shows almost linear elastic until failure over here, and then slightly more deformation over here. We noticed throughout the course of all 8 experiments that we had a clear differential between the flat printing build orientation and the vertical build orientation. And in the graph down here, you can see that there's clearly much more energy absorption in the functionally graded core. And then even in the uniform core, when it snapped, we were below 5% elongation here, which shows that this might be a brittle material. And then this could be a ductile material over here with the yielding zone and the actual break. We weren't expecting that based on the data sheet. Now, for plotting just our comparison with our FEA results, again, we only did 1 millimeter displacement in the FEA, so we extrapolated that out 5 times so you could see it. It's correlating pretty well with the data that we had here for the functionally graded core as well as uniform core, especially in the vertical build orientation, extremely close. All right, so now flexural stress and flexural strain. Let's convert for it. Here we go. All right, so when we pull these guys out, the functionally graded core material down here, it's showing less of a modulus, which was expected, but it also took a lot more strain. And then again, we're really showing a difference here between flat and vertical. It's showing like ductile versus brittle. The max stress was much lower in the constant throughout when compared to the functionally graded core. So we'll investigate that a little further. All right, our actual flexural modulus itself. You can see the uniform core was winning. Our functionally graded core was less, but we need to normalize that. We've got a much lighter sample here. In order to make it fair, we take out the density, and now we've got a functionally graded core that even if in its worst build orientation is coming in 10 to 12% higher when we get the performance factor. So, and then comparing the vertical build orientation, now we're seeing some good stuff. So let's compare that numerically to our numerical estimation, our analytical estimation. Now we're clearly seeing a difference here. Again, we'll get into the ductile versus brittle here, but in the vertical build orientation, we're getting an overall percent difference of 0.65% between the experimental and the finite element analysis, and an overall 6.6 between all 3. The vertical build orientation is definitely leading to an enhancement in the performance, which is an excellent validation of our hypothesis and results. All right, but overall, for the elastic plastic portion, we're getting better stiffness. But meanwhile, let's look at the actual strength. The strength, we knew this was going to happen. The strength suffered a lot. So this is going to be a major design trade-off and something we'll leave for future works. The stiffness to weight ratio versus strength to weight ratio. Build orientation, again, played a factor here as well, but the overall numbers were proportional here. Functionally graded core did come out weaker due to a failure mode transition, which we'll be able to show in some of the later pictures. But overall, in the constant density samples, we had a face yielding, which the faces of the actual core broke, or the faces actually broke by the core. And then in the functionally graded one, we had a core yielding due to core shear and then eventual core collapse from the compressive forces. So the shear strength drop at the neutral axis overall led to these results, but we also noticed a progressive failure, which led to secondary effects of energy absorption, which is awesome. We're going to investigate that in a little bit. All right, so now let's look at these results in depth for why one was ductile or versus one was brittle, and actually prove that. First telltale sign is going to be the break. So we've got the flat printed sample on the left and the vertically printed sample on the right, printer orientation wise. In the left sample, you can see immediately once it gets past the face sheet, it goes just beelines and a 45, almost textbook ductile breaking. Whereas on the right side, our fracture is 90 degrees. So again, textbook brittle. Coming in over here, we see a more rougher surface, not quite as shiny as the one on the right. Shiny versus is going to be more brittle versus ductile over here. And then lastly, if you look over right here, we've got some minor mist marking that you can see over here, and that's kind of mirrored over, also being a telltale sign of a brittle fracture. All right, and then here, right off the bat, you can see this guy splitting off and flying into oblivion. And it is even giving itself away right there, vertically variable geometry. This guy's clearly brittle based on the failure nature. And then over here, textbook gross plastic deformation, which is #1 ductile failure. So in the flat build orientation, you can, this is really cool. You can actually see the failure in here. You can see the shearing and the direction that these center struts are going. And then we also see that progressive failure in here. So we've got a failure of the center near the neutral axis, and then we get a failure of just complete failure at the neutral axis, and then just core collapse right here after the shear stresses, the compressive stresses come in and just crush that. We move on to the next layer of core density that breaks, and then we finally have face yielding at the top, and then the bottom breaks with face yielding. But it's still mechanically connected, which is amazing, and which is going to be great for some other stuff, which we'll talk about in a little bit. All right, so now that we've moved through the layers here, let's move on to showing this, plotting it mathematically. So first, we can easily find the energy absorption. We're just going to integrate the area under these curves, and that area is going to be the actual flexural energy absorption. On the left sample, you see it starts, the figure A corresponds to capital A being at the origin, coming up to B somewhere in the center, and then C, our ultimate failure, and then goes out of frame. We don't actually see the failure. Whereas in B, this is really cool. You can actually see the points of failure and how it would recover in between and continue holding, absorbing all that energy. So D, again, origin, and E, you see the initial failure where you lose the flexural strength, but you're still coming through, and you've got F where it fails again at the second row of density. And then you can see where it crushes the next layer, and then G where you initially come up to the face yielding, gaining again until H where you have a complete failure. So catastrophic failure right off the bat, and then progressive failure down here. All right, so pretty neat. Now, categorizing this in specific energy absorption, which has been, again, normalized for the density, we can show, before specific energy absorption, you can see that the normal energy absorption in the uniform core is higher, but now we're going to take the density out of that, normalize it again, and we show that overall the flat build orientation is almost the same, with the functionally graded performing slightly higher in both instances on the flat orientation, and same functionally graded barely higher in the vertical print orientation. So again, a design trade-off, and we attribute this to the progressive failure versus the catastrophic failure, and the build orientation is definitely most likely the driver between the ductile versus the brittle orientation. Uses for this in industry: spacecraft, micrometeorites coming at satellites. We want something that's going to be able to take numerous hits, hit after hit, and not have a catastrophic failure. We'll be able to absorb that energy and then continue taking that energy, so we don't have to send up repairs or anything. And then this will end up going into high performance aircraft, race cars getting hit by stuff, debris, thought impacts on aircraft, and then impacts to pilots or drivers in cockpit regions as well. All right, so in summary, we were able to manufacture these sandwich beams through a single manufacturing process utilizing the PolyJet 3D printer. The Stratasys J55 was capable of creating repeatable sample qualities with similar defect densities and microstructures. The hypothesis was proven through FEM, and then again proven through experimental data. And we had a functionally graded, ended up having a higher stiffness to weight ratio. The numbers in agreement, you can see an increase analytically of 33.1%, 31.9% numerically, and then 31% flat for our experimental results. So the data is in agreement. We had a great experiment, and we also found that there was a lower strength, which we knew was going to happen. So a design trade-off there for future work. And then we also found the progressive failure possibilities in the functionally graded beams. Finally, we inadvertently found an awesome specific energy absorption in the flat build orientation, which was slightly higher in the functionally graded samples. All right. Thank you all for coming. Dr. Gordon, I'd especially like to thank you for sitting as chair, especially considering the unconventional nature of me being an online-only student. I really appreciate the risk that you took with that, and your mentorship and support throughout. I hope to meet you in person and shake your hand at graduation. Dr. Yavas, I definitely couldn't have done it without you. you're willing to help me from the beginning when I told you I wanted to do a thesis, and you also did this online only with me as well, and you shared the same enthusiasm as I do for science. When I got stuck, you're always there, you always knew what to do, and I never felt alone through this research. Even when you switched universities, you still stuck with me, and I'm glad we were able to get together for the experiment. That was a lot of fun, and I'm glad we could share that. And it's been an absolute pleasure. And Dr. Wu, thank you so much for serving as a committee member. I know you stay really busy, and I really appreciate you taking the time to be here. I'd also like to thank the UCF Innovation Lab for allowing us to use the Stratasys J55 for this thesis. I know they're not cheap, and I'm really glad we had that on hand. And I'd also like to thank my mother, who's been there for me my whole life since the beginning, all her love and encouragement, and giving me the eagerness to learn and the drive to excel, and also for randomly proofreading and all the grammar corrections. And then also like to thank my wife for all her love and support, keeping motivated, and also for watching our 1-year-old Natalie, who's wild right now while I finish this up. And thank you to all my friends, family, and mentor who tuned in and watching. I really appreciate you being in here, and I truly appreciate your support, interest, and all the motivation throughout the years. All right, I'll give the floor back to you, Dr. Yavas.
Thank you. Excellent piece of work, and I like to thank you. I really appreciate your hard work. And so is there any general question from the general audience?
I do have a couple of specific questions if Tim is willing to jump back slides, but I don't want to interrupt whatever you're doing, Professor. So you let me know if it's the right time for that.
I think we have some time for the general questions. Please go ahead. Yeah.
I believe it was about slide 13 or 14. If you could jump back there, Tim.
Yep. All right, approach or later? Here's 13 coming up.
Go forward one. All right, sorry, it was back, so it could have been 12.
Ah, okay.
Yes, this is the slide. I wanted to ask if the previous studies done by other persons had taken into account how the temperature difference as you move away from controlled temperature beds in certain printers might have affected this.
They did not. From what I found, they both utilized object brand printers. That wasn't a major consideration. And even when he was looking at the age of the print, that was an afterthought that he found afterwards, just by not doing the experiments at the same time. But that would be interesting to do in the future.
Okay. 42.
Oh, yeah.
So this was a really neat video. I wanted to ask, the standard ASTM test, does it take anything into consideration for edge cases? I know that in core materials like this, and probably functional materials, as you're saying, that can really affect the performance of a unit. So in other words, had this sample size been significantly larger so that you were operating the test on a quasi-infinite sample, do you think that it would have changed the performance?
It did not specifically take that into account. The geometric constraints that we put on this of the 6 inches were in line with that. But I do believe if we made a just infinitely long one, I think it would have waited a while to at least potentially to shear. You mind if I swap slides really quick? Let's go to the pictures here. So right here, you can see where the shear forces are taking it out right here. But I'm not sure that I know it would have taken a lot longer for core collapse to occur right here, because this is just compressive nature smashing it. I do think it would have performed better, and if the printer was bigger, I would have loved to try it.
Understood. So on to slide 45, you talked about the normalization here. Obviously, this is important for the calculations to show the performance of the materials, but have you learned anything, or would you suggest anything to other persons about staying away from the edge cases on the printer's ability, or what manufacturing processes might you use to get some more of that excess build material out?
Definitely. There's a lot of other printers out there. One that we specifically looked at was using one of the EOS printers and printing these in stainless steel, in which there wouldn't have been much support material. A lot of post-processing on the back end, like machining it off the build plate, but making a significantly stronger strut inside, and then potentially just bigger geometry in general than our super fine geometry in this functionally graded core. Probably would have made the results a little better, but that would have been well outside of the budget for a non-funded project.
Oh, jeez. Okay, I had one more question about that. So I wanted to say, this study is really cool, and I was wondering if anyone is planning on continuing it, if they were going to do an analysis of the different, call it densities of the core sizes. So for example, you just did a half, half, half. Perhaps there's, asymmetric and or even just different ratios that would perform better than others.
Oh, definitely. I plan to continue this with different face sheet thicknesses, but there's definitely room for, based on previous research, whenever asymmetric linear cases were covered, there wasn't a major increase in stiffness. But if it was truly asymmetric, who knows? That's definitely a question that's still out there, and I personally like to see the answer.
That's all for me. I think this was really cool, Tim. Really glad I tuned in and got to see it.
Thanks. And thanks for staying. I appreciate the questions. It's good food for thought.
Are there any other questions?
Hey, I just had one, if I can indulge Tim for a quick question.
Oh, for sure.
So I had the advantage of getting to go to Penn State for one of their additive manufacturing training conferences. And one of the things that they do to verify their materials is basically the equivalent of like a CT scan to sort of see what's going on the inside. In your literature review or anything like that, did you come across folks who are, as they're preparing these materials on the additive side, kind of looking at, what's going on the interior of your print?
Oh, that's a really good question. I did not see that when it was related to polyjet printing, but I think I remember catching one article where they did that with printing and through either SLA or SLS of metallic prints when they were combining the different densities and different materials in there. But they were mainly investigating the cracks that were already there, pre-cracking and stuff. But I wish I could throw these in there. I'd love to see the microstructure, an X-ray of these things.
Yeah, it would have fleshed out some of that inward material that was left on from the support and things like that. You could have seen what was there and all that sort of stuff. But either way, great presentation. Thank you.
Thank you. I'm glad you're here.
Well, if I believe if there is no other question from the audience, we will need to ask them to leave, I believe, and the rest of this session will be restricted to committee. Thank you very much for your attendance, and we appreciate it.
Thanks, everyone. Appreciate it.